Hello, welcome back. Today it's going to be a little bit different. Instead of solving a bunch of homework questions, I'm going to cover a concept in mathematics that you will probably see for the rest of your math career, especially in the near future for some of you, and that concept is the unit circle. Before I do that, I want to look at a right angle triangle first. So I'll draw this. I'm going to label this triangle a little bit differently. Normally you would call this A, this B, and this C, but I'm going to use different variable names, and you'll see why, but just stick with me here for now. I'm going to call this bottom angle, this bottom side I mean, X, this leg here Y, and this hypotenuse here R. I'm also going to name this this angle here, theta. Now, we're going to solve for X and Y in terms of trigonometric functions and R. So first, we know that the sine of theta is equal to the opposite over the hypotenuse. In this case, the hypotenuse is r and the opposite is y, so we have sine of theta equals y over r. And solving this for y, we get y equals r sine theta. Same thing with cosine. Cosine of theta equals adjacent over hypotenuse. And we have that x equals r cosine of theta. Now, we're going to write the Pythagorean theorem for this triangle. We're going to say that a squared plus b squared equals c squared. This is the formula we all know. And we're going to define a as x, and we're going to define b as y, and we're going to define c as r. So now we have x squared plus y squared equals r squared. Then we're going to take these values that we got for x and y, and we're going to substitute them into this. So that gives us r cosine of theta squared plus r sine theta squared equals r squared. Squaring each of these terms gives us r squared cosine squared theta plus r squared sine squared theta equals r squared. We see that in this left side, both of these terms have an r, so we can factor it out. R squared times the quantity of cosine squared theta plus sine squared theta equals r squared. And finally, we have the cosine squared theta plus the sine of theta squared, sine squared theta equals 1. This is called the Pythagorean identity. This is a very powerful identity. And the work we also did to get from that triangle to this point is also very important. It allows us to do a couple of things. First, it is a very nice introduction to polar coordinates, although you won't touch that until pre-calculus or even maybe in calculus. But this is a very nice introduction to polar coordinates, and it also allows us to construct what is called the unit circle. Note that in the word unit circle, the unit refers to 1, and that 1 is talking about the radius. So it is basically saying, the unit circle is basically saying that it's a circle of radius 1. And we'll see why that's relevant later. looking at this, we can rewrite the equation above, r squared cosine squared theta plus r squared sine squared theta equals r squared. This will still be true if we set r equal to 1. So if we set r equal to 1, we see that this r squared becomes 1, this r squared becomes 1, this r squared becomes 1, and we get cosine squared plus sine squared equals 1 again. So with this knowledge, we can draw a new triangle, this time of radius r, and now with the base, hypotenuse r, cosine, a base of cosine theta, and a height of sine theta. Now, because we know that cosine squared theta and sine squared theta added together is equal to 1, regardless of what theta is, we can confidently say that any value of theta will make this triangle true. Any value of theta at all will make this triangle true. So instead of, okay, we won't call this r. We will call this 1, just so we keep things consistent. Since we know that cosine squared theta plus sine squared theta equals 1, any value of theta will make this true. Before I get into the visual that describes what I'm talking about here, I want to talk about one last thing. So remember, if you're given a line like this, you can find the slope of it by calculating the change in y over the change in x. And you were told that the change in y is this bit here, the change in x is this horizontal bit here, and that the slope forms a triangle where the hypotenuse is the line itself. This here works exactly the same way. For example, if this height was 5 and this base was 10, you would find the slope by doing the change in height, 5, over the change in base, 10. In this case, the base, the change in x, is cosine theta, and the change in height is sine theta. So your slope is the sine of theta over the cosine of theta, which you could actually rewrite as the tangent of theta. But I'll use sine theta over cosine theta just to really drive this point home. So if you were to actually write the line, you would write y equals sine theta over cosine theta x, where theta is any value, and the value of theta changes the direction that this line points in. So let's get this here. So now, so now we have y equals, actually I'll set this t equal to like 30 or something. You can't use theta for some reason. It won't let you use that. See, so I'll use t for theta. So now here we can say that y equals the sine of t over the cosine of t x. And just so we don't draw a circle that's ridiculously long, we will set a domain here like that, so that the length of this is always 1. Now observe how as we change the value of t, or theta in this case, we will draw a circle that goes all the way around. Look at this. Oh, hold on, I might need to draw a second one. Aha, okay. Now have a look at this. Hopefully this will work. Brilliant. Look at that. Circle all the way around. And notice the length of this is always going to be 1. Like, I'll move it up here. See, the length is 1. Why does it disappear? I guess it's fine. It always has a length of 1, constantly. This is where the unit circle kind of comes from. I'm going to draw a couple more lines. I'll be right back, because this will take me a moment to get written, but it will make a lot more sense when I actually do get those lines drawn. Alright, so now what I've done is I've actually drawn the circle that we're going to be using. And I've actually drawn also some lines that you'll see. Now look at this. Look at that. See how those lines always form a right triangle? It's always a right triangle. This is kind of where the unit circle comes from. It says that no matter what the angle of theta is for the side lengths, for the angle here, because let me stop this real quick. This angle here, no matter what value of theta you put for this angle here on the inside, the cosine of theta squared plus the sine of theta squared will always equal 1. The hypotenuse here. And the point of the unit circle is to show that property. Now, we could use degrees, but there's also another unit of measurement called radians. Now, radians are like degrees, but they use values of pi instead of literal degree markings. I have found this diagram online that kind of shows the point. So you see that every single one of these angles has their own radians. Going back to this, we can then say 30, and then we can say that 30 degrees is equal to pi over 6. And right now it doesn't look like it's the same, but remember that we need to actually convert this to radians. And look at that, it's all the same. You can actually slide this along. See, from 0 to 2 pi. And we can draw a circle like this. So that's pretty much the unit circle.